Hello, this is David Bieberman, CTO of Prasaga. Today we're going to talk a little bit about the Extensible Blockchain Object Model, or XBOM, the object and class concepts, how they're implemented. This is implemented on top of Hyperledger Fabric currently. In a previous video, walked through a little bit of how that gets bootstrapped and run. It's worth watching that video as well. All objects and classes follow what's called a first-class object model, and what's also known as late dynamic binding. What this means is that all objects have an object reference, all classes are referenced by an object reference, and all meta-classes are referenced by an object reference. It also means that a meta-class creates classes, and a class creates objects. It means that classes can be inherited, just like you would expect, and meta-classes can be inherited, creating new classes that create classes. The object handle, the object reference to any object, is a generic type. That means that an object handle can reference any object or class. There are ways to cast that appropriately to the class that you want to operate with to provide signature matching during compile time. But in general, any object handle can point to any object. The account model created by Hyperledger Fabric, the account model created by the XBOM on top of Hyperledger Fabric is created by the foundation classes. We'll walk through them. Every object is contained within an account object, with an account object essentially containing itself. And to bootstrap, there is a system account object that contains the root account objects, which would be class object, which is the root for all objects, including classes, and class, which is the root for all meta-classes that create classes. As noted, all objects and classes inherit indirectly or directly from class object. The class manager infrastructure, which enables the first class object model and late dynamic binding across the Hyperledger Fabric, is implemented as standard chain code as far as Hyperledger Fabric is concerned. It uses the minimum version of Hyperledger Fabric must be 2.0 or higher. The reason for that is it takes advantage of something known as external chain code. As was shown in the previous video clip, to enable class manager infrastructure goes through three phases. The first one is it loads as standard chain code, as was noted. The second one is that the init call, which is a part of Hyperledger Fabric chain code loading, initializes three built-in classes: the class object, the class, and the class dictionary. This is the root to enable everything to work. And then there's a one-time transaction that's sent to the class manager infrastructure as a separate function called init bootstrap. This only needs to be done once when the blockchain is first brought up, not when you bring up individual peers or nodes or anything like that. It'll never need to be run again, and it's no material. If it is run again, it doesn't do anything. What it does is it brings up the XBOM application class framework. It loads those classes permanently into the blockchain. What we're going to do is talk about a handful of classes, then show a little bit about what a class looks like going through this. This is not a complete inventory of all the classes. And of course, in this type of environment, new classes can be added all the time while the blockchain is running. Class factory follows what's known as the factory design pattern for object-oriented programming. The factory design pattern means that you've created an object whose job is to create objects of a class type that's stored within it. To accomplish that in this type of first-class object model, all that's necessary is that the object reference or object handle to the class that the factory object should create be stored within its instance data. Then methods are part of the class factory to create new instances of the class whose reference is stored in the instance data. Very straightforward. This is directly used by the class account manager, which subclass is from class factory, and is used for the ability to create new accounts. The base class environment, which again was in the previous video, uses class account as the class that class account manager would create new accounts with. However, the intent is that accounts would be, account types would be subclassed from class account to accomplish specific types of behaviors. For example, there would be a class supply chain account intended to be used by supply chain use cases. Then an account manager instance would be created with that account type in it, so that messages sent to that account manager instance would create new accounts of class supply chain types. Once an account is created, we want to create a containment concept where the account logically contains objects within it. And this is to create something analogous to a process model. You think of an account as a process, and the objects contained within it would be objects within your process. This is an analogy because it's not exactly the same thing, but it's a reasonable approach to consider. The class XBOM container objects store a list of the objects that they own or contain. They're in a list. Because the object handle, again, is a generic type, this means that any class that inherits from class XBOM container and thus has containment capability can contain any type of object. And there's an API to tell what type of class any object belongs to for any sort of iteration or capability like that. More importantly, all accounts, because class account inherits from class XBOM container, are by definition containment objects. This matches up with the model of an account being analogous to a process. So as a result, an account can contain objects, and any object that also inherits from class XBOM container can further contain additional objects. This enables a tree structure inside of any account. And further, if there's nothing, because it's all done by object reference, there's no prohibition against creating cyclic trees. It's perfectly valid to do that. Any sort of iteration across the tree, of course, has to take that into account, and that's accounted for so you don't end up with infinite loops. The class dictionary function enables the translation from human readable unique string names to ledger object IDs. The ledger object ID is a 32-byte secure hash 256-bit value. It is guaranteed to be unique across the ledger database on the blockchain. Always. Once a ledger object ID is created, it is unique forever. Once an object is stored with a unique ledger object ID or LOID, it will always be referenceable by that ledger object ID. However, the user, a client, needs a way to get the ledger object ID. To enable that, a root dictionary is part of the bootstrap behavior, one-time bootstrap, and it will contain string names mapped to LOIDs, and it's retrievable by a direct function query to the class manager infrastructure chain code. It's always available to do that. Once that ledger object ID is returned, that can then be used. You can now send messages to the dictionary object to receive translations from the string names to the ledger object IDs of the object you're interested in. In fact, this coupled with the second function, the class manager infrastructure query that enables you to also retrieve the system account object, enables you to bootstrap any sort of interface with the blockchain. Also, most importantly, you only need to retrieve the root dictionary ledger object ID once as a client, and you only need to retrieve the system account object ledger object ID once. They never change ever once the Hyperledger Fabric blockchain has started. So for the life of a blockchain, the ledger object IDs are constant. Now we'll talk just a quick overview of the Go language class files. All classes in Hyperledger Fabric XBOM are implemented in Go currently. Go's programming language, it's called Golang. It's an open source language, and you can find it on GitHub. The file structure, the class structure consists of three important files. One of them is the class implementation file. This is where you implement the methods of your class and define the instance data for your class, for the objects of your class. The second file is a stub file, which provides the interface for other classes to call methods on your class. And the third file is called a skeleton file. And what that is used for is that the class manager infrastructure calls the functions and methods in this file, which in turn call the actual class methods that you've implemented. These three files make up the basic structure of a class. Currently, the developers create all three of these files by hand. A future version would generate the stub and skeleton files with a compiler. That's on the list, that's on our roadmap for Prasaga. Let's talk a little bit about the semantics for calling methods. There's, again, following the analogy of a process model for an account, there's two ways to call a method on an object. First one, when you do a straight, what's called an object call, the code for the object, the call to the object, executes in the context of the current calling account. So it's as though you're running within the same process. When you do an object send, or you send a method to an object, that transitions to the account context of the called object. That's how you would transition from one analogous of one process to another, in other words, one account to another. This makes it possible to do inter-account messaging within a transaction, and you can pass any data needed. When the client is calling into a method on an object or sending a method on an object, both are valid. It needs the following parameters are there. An internal opaque object context. This is what's used for interfacing to the class manager infrastructure. And we'll show just a little bit of the data types in another slide. You pass the account object that the object's contained in, the target object where you're calling, the method name for message resolution, what method are you calling, and input arguments. And the input argument is a single pointer to a data structure. In all, calls and sends return a pointer to an output data structure and an error value. In the previous video, I walked through a flow graph of how a transaction is processed. You can refer to that for the details of that part. Now let's take a short look at the signature of a method, because this is the key part of what a developer would write. The syntax for every method essentially looks the same. And it's all the pieces are called out in this diagram. In Go, the way a method is defined is it uses the term func for function, but then it puts what it calls a receiver in parentheses before the name of the function. This is what makes it a method. And for the XBOM environment, that receiver argument is always a pointer to the instance data of the instance data type defined by your class. It's passed in, and all you have to do is, all your code does is do operations on that instance data. So this is how the data is passed. This is the state maintained for every object. It should be noted that the instance data for your class is only the instance data that you've defined in your class. Your ancestor class's instance data are not directly available. You can access them through method calls for your ancestor classes. And there's a method called object call ancestor that literally calls the ancestor to pass parameters to it. The next part is the method name, which is a straight string name. It's standard source code. And that's what is used to resolve in the method table, which again your class defines from the messages being passed in by a caller to the method to call. The first argument passed in, the first argument in your signatures, the syntax for your signature always is an opaque pointer to what's known in Go as an interface to the class manager infrastructure methods. I will show what that table looks like. This is the interface that all classes use to interface with class manager infrastructure. The next argument is a single pointer, always one pointer to the input argument structure. And that's what all the arguments, anything passed into a method is sent that way, and then it's returned. The return is a pointer to an output argument structure, again defined by your class, and an error return value of type error. Error is a standard Go data type. The body of your method usually starts with a definition, variable, actually technically declaration of the output arguments as of the output argument struct type, and a variable for the errors, usually termed ERR. The body of your method then uses the input arguments in your instance data to perform whatever the function is, as well as any calls to other class, any objects in any of their accounts and classes. And whatever the result is returned as the pointer to the output arguments by taking an address and the error value. Every method of every class looks like this. Now what we're going to do next is take a quick look of the actual source code for the class manager intrinsics infrastructure interface. And a little bit, we're just going to go take a look at the implementation for class XBOM container as an example. This is our GitLab server where the source code for the XBOM implementation currently is. I'm going to walk through a couple of capabilities here. GitLab is the open source version for GitHub. First, let's take a look at the class manager infrastructure interface. This is something that all classes would compile with. There's some bookkeeping things in here, what a method definition looks like, some administrative functions your class has to do, those types of things. We'll define those later. For the core of your work, your classes would use this interface with the object context it's passed in. We'll show that in a minute. There's an object call ancestor, object send. Notice that all of these use what's called interface with empty brackets. In Go, that's kind of the equivalent of a void pointer in C or C++ or other similar behaviors. One of the things that these stubs and skeletons do, which we will show, is provide type information so that when you're at compile time, when you go to make a call on a object of a class, the argument type checking for the input argument, output arguments happens. Note that because all objects in the end are referenced by a generic object handle type, when you send a message to an object, it's perfectly valid to be sending a message that there is no method that implements it. What will happen is you'll get a return error saying not implemented. That's not a runtime error. That's not a crash error or anything like that. That's standard behavior. It's perfectly valid to therefore send messages because of late dynamic binding that are not implemented by a specific object. It's very useful for iterations across heterogeneous lists of objects. The getSelf returns the object handle for the object you're currently in. Make new object is generally an internal method. You don't really need to use that. That's actually part of what the meta class uses. Then various things. Get the current account, who currently owns you. A translation from your internal object handle to the actual 32-byte ledger object ID that is the reference in the state database, and so on. We've also implemented direct access to the Hyperledger database. I would note that these layers down here, these functions down here, are not needed for normal class behavior. Your instance data of your objects are transparently stored in the blockchain state database and distributed accordingly with standard Hyperledger behavior. Even the instance data for your class is stored that way. These functions are if you want to access other types of records that are stored in the database, and there's nothing stopping you from doing that. Further, if you want to make sure that the key to any record that you put in the database is also unique, you can get a new ledger object ID with this function, which is guaranteed to be unique on the blockchain. Now, let's take a quick look at a couple pieces of class implementation, give you a taste for that. We're going to look at class XBOM container. The first thing I'd note in class XBOM containers directory is that there are multiple stub files for other classes that class XBOM container makes calls on, either as a self-call or of other objects. Now let's go into the implementation for it first. What I want to focus on here is what a method actually looks like. So as we showed in the anatomy of a method previously, here's the actual instance data pointer. Here's the method name. Now we'd note that the rest of this is by convention. That's not necessary. It just makes it a lot easier when you're writing your code to understand whether you're in implementation or in a stub or a skeleton. Here's the object context. This is your interface to class main or infrastructure. This is your input arguments, pointer to your input arguments. Here's your output argument pointer, and here's an error return. Let's go look at the body. Here's the output argument definition. So declared an argument of type class XBOM container insert child out args. In this particular case, I'm doing an insert child, which means I'm inserting a child object. So I'm iterating over my instance data. Here's my instance data of children, and verifying that it's not already there. If it's there, I just return valid. I return the handle. The syntax, the semantics of this is just return a value. There is no all error. Nil is means no error. All errors are returned as nil. Nil is the equivalent of null in languages like C or C++. If I was unable to find the child already inserted, I simply insert it with an append, which inserts it into this array, and then I again return the output. Similarly, there's a remove child, and there's a get child, etc. And then there's various bookkeeping type methods that are needed as well. As a quick look, every class defines the method table for the class. This is what it looks like. In the future video and documentation will explain the details of this. It's not very complex. That's what it takes to do a method in a class. I believe at the top I can actually show you the instance data structure for this, which is right here. And this is the instance data structure definition for all classes, all objects of type class XBOM container. And it literally is the variable children this is syntax for what's called a slice of containing object handles, which again, any object can be referenced by an object handle. Now let's pop up one more, and let's just take a quick look at what a stub looks like, what skeleton looks like. This is what a stub file looks like. It has the type definitions for the input and output arguments. It has a stylized method that looks like this. What's special about this method over the implementation method is that the receiver is the class for the object. It's a class type for the object. Remember that an object handle is generic. However, you can create essentially equivalent of a type alias to a specific class. The reason why you want to do this is this enables compile time type checking of the input argument type and the output argument type and the return argument types, so that the caller to an object of a class knows that it's actually sending the right argument to the right method and receiving the right argument type back. In a late dynamic binding system like XBOM, these types are normally not checked at compile time. This usage of Go language syntax enables a type of type checking for a late dynamic binding system that eliminates obvious errors where you're literally passing the wrong arguments to a method or expecting the wrong arguments back from a method. This is a very powerful capability that's enabled by simply creating these stub files. If you'll notice, in class XBOM container, back in there, we in fact compile with multiple stub files. You'll notice that there are several other stub files that are compiled with the class XBOM container implementation, which are in fact these receiver methods, as I'm just showing, for each one of the classes that it might be sending a message to, or to its ancestors. And let's just go back and take a quick look at the code because you can see the cast going on. And let's take an example of this right here. So what we've done here is we've retrieved a dictionary object. It's actually for the class type. It's returned as a standard object handle. That's one of the output arguments. Again, that's a generic handle. What we do is this syntax says cast it as a class. This is a cast syntax for Go. It's a little bit different than you're used to, say, for C, C++, or other languages. We now have essentially an object handle that is cast as class. When we go to use it, we go to send a message, we can now use standard syntax as though that's the object type. And here's an example of doing that. Here's the object handle. Here's a call on a message. And here's the syntax for it. The object context always has to be passed. And the arguments, pointer to the arguments. Of course, and then it returns an argument type. Okay. Again, you can see this being done down here as well. Okay. And as a result, when you're writing a class implementation, using this method of casting your object handles to the class of the method that you want to send a message to, you eliminate at compile time common problem sending the wrong arguments to the wrong method or receiving the wrong arguments. It's a very powerful feature, very easy to use, standard Go syntax capability. So worth pointing out too, we use that very heavily, and it makes your code much easier to read. And I believe that wraps up what we had intended for blockchain for this overview of XBOM concepts. And let me back up to, if you'd like to contact us, more information about Prasaga and the XBOM implemented on Hyperledger Fabric and uses for it, and our intentions to make the class interface available as open source. People can add their own classes and then use this in their own Hyperledger Fabric chains. Please reach out and contact us. Thank you very much.